What if the moon isn't what you've believed your entire life? Welcome to Sleepy Space. Tonight, we'll drift beyond the familiar glow of moonlight and uncover the moon's astonishing true story, from its violent birth to its hidden influence on Earth itself. Before we begin, please like, subscribe, and let me know in the comments where you're listening from and what time it is where you are. Now, settle in, relax, and let's begin our journey. Imagine stepping outside on a quiet night long after the noise of the day has dissolved into the distance, long after the roads have emptied and the last glow from neighboring windows has begun to fade, and lifting your eyes toward the moon, that familiar silver companion that seems so ordinary we rarely pause to question it. It hangs there with such effortless calm that the mind almost files it away as part of the background of existence, like the color of the sky or the rhythm of breathing itself. Yet the strange thing about familiarity is that it often conceals complexity. The more frequently we encounter something, the less likely we are to ask what it truly is. For most of human history, the moon appeared to be exactly what it looked like, a luminous object drifting across the darkness, changing shape from night to night, governing myths, calendars, harvests, and stories. Even today, despite centuries of scientific discovery, many people still carry an intuitive image of the moon as a kind of celestial lamp, a decorative light suspended above Earth. But the deeper one looks, the more that image begins to dissolve. The moon is not a lamp. It is not a symbol. It is not merely a backdrop to human history. It is a real world, a physical place with its own geography, structure, history, and dynamics. A world whose existence has quietly shaped the evolution of our own planet for billions of years. The first step toward understanding the moon is recognizing how profoundly different reality is from appearance. To the naked eye, the moon seems large, yet it is actually much smaller than many moons elsewhere in the solar system. To the naked eye, it seems bright, yet its surface reflects only a modest fraction of the sunlight that reaches it. In fact, fresh asphalt reflects a surprisingly similar amount of light. The moon appears luminous, not because it is highly reflective, but because it floats against the immense darkness of space. This subtle distinction reveals an important principle in astronomy. What we perceive directly is often less informative than the physical mechanisms producing the perception. The moon shines because sunlight travels approximately 93 million miles from the sun, strikes a rocky surface covered in fragmented dust and ancient debris, and then reflects back across nearly 250,000 miles of space before reaching a human eye standing somewhere on Earth. Every moonlit night is therefore a demonstration of geometry, optics, and celestial mechanics operating with extraordinary precision. Even the phases of the moon, among the most familiar sights in the sky, reveal how easily human intuition can be misled. A crescent moon is not partially illuminated because Earth's shadow is covering part of it. That explanation feels natural, but it is incorrect except during a lunar eclipse. Instead, the phases emerge from changing viewing angles within the Earth-Moon-Sun system. Half of the moon is almost always illuminated by sunlight. What changes is our perspective. As the moon orbits Earth, the angle from which we observe the sunlit hemisphere shifts gradually, producing the elegant sequence of crescent, quarter, gibbous, and full phases that have marked the passage of time for countless generations. Hidden within this simple cycle is a profound lesson about the universe itself. Reality often depends not only on what exists, but on where the observer happens to stand. The moon's orbit around Earth is equally deceptive in its apparent simplicity. Looking upward, one might imagine a perfect circle traced across the sky, yet the actual motion is a far more intricate dance governed by gravity, inertia, angular momentum, and the curved geometry of space-time described by modern physics. The moon travels around Earth at an average distance of roughly 384,400 kilometers, but that distance is constantly changing because the orbit is slightly elliptical. Sometimes the moon drifts closer, appearing larger in the sky. Sometimes it moves farther away, shrinking subtly. These variations are small enough that most people never notice them consciously, yet they are measurable, predictable, and deeply revealing. They remind us that celestial objects are not fixed ornaments, but dynamic participants in a continuously evolving gravitational system. As scientific understanding expanded during the 17th century, The moon gradually transformed from a philosophical mystery into an object of physical investigation. When early telescopes were turned toward it, observers discovered something astonishing. The moon was not a perfectly smooth, heavenly sphere, as many ancient traditions had imagined. Its surface was scarred, uneven, mountainous, and complex. Craters cast long shadows. Jagged ridges interrupted vast plains. The moon possessed landscapes. This realization may seem obvious now, but at the time, it represented a profound shift in humanity's understanding of the cosmos. The heavens were not fundamentally separate from Earth. They were physical places governed by physical processes. In a sense, the discovery of mountains on the moon helped initiate the intellectual journey that eventually led humanity to modern planetary science. Yet even telescopes revealed only part of the story. As the 20th century unfolded and spacecraft finally crossed the distance separating Earth from its companion world, a far richer picture emerged. The moon turned out to be neither a simple rock nor a static relic. Beneath its dusty surface lies evidence of a complex geological history. Ancient impacts reshaped enormous regions. Vast lava flows once spread across colossal basins. Layers of crust formed, fractured, and evolved over immense stretches of time. The moon that appears motionless tonight is the surviving remnant of processes so energetic that they challenge imagination. This realization invites a deeper question. If the moon is a world, what exactly defines a world? Traditionally, people reserve that word for planets, yet planetary science approaches the matter differently. A world is not defined merely by classification. It is defined by physical reality. A world possesses terrain, structure, history, and interaction with its environment. By that standard, the moon unquestionably qualifies. It has mountains taller than many found on Earth. It possesses valleys, basins, impact structures, and regions with distinct geological origins. It has a measurable internal structure consisting of crust, mantle, and core. It experiences temperature extremes capable of transforming the behavior of materials. It occupies a unique position within a larger gravitational system. In other words, the moon is not merely orbiting Earth. It is living out its own planetary story. Perhaps the most fascinating aspect of this realization is how it changes our perspective on scale. Human intuition evolved within forests, plains, coastlines, and mountains. Distances were measured by footsteps, rivers, and horizons. The moon challenges those instincts. The nearest major celestial body to Earth is still so distant that every human who has ever traveled there would fit comfortably inside a small auditorium. The average gap separating Earth and the moon is large enough to fit all the planets of the solar system side by side, with room remaining. This is not merely a numerical curiosity. It reveals how empty space truly is, and how extraordinary the Earth-Moon relationship actually becomes when viewed against the vast backdrop of the cosmos. Many planets possess moons, but few possess one so large relative to the planet it orbits. This proportional relationship makes the Earth-Moon system unusually balanced, almost resembling a double-world configuration when viewed through certain dynamical frameworks. The consequences of that relationship extend far beyond appearance, influencing tides, rotational behavior, and long-term planetary stability in ways we will explore later. For now, what matters is recognizing that the moon is not a passive object suspended in the sky. It is an active participant in a gravitational partnership that has endured for billions of years. And perhaps that is the quiet revelation hidden within every moonlit night. The moon appears simple because distance softens detail. It appears familiar because it has accompanied humanity throughout recorded history. It appears gentle because its light arrives silently. Yet beneath that calm exterior lies a world of extraordinary depth. A world with its own landscapes, its own chronology, and its own place in the larger architecture of the solar system. The longer we look, the more the old image of a glowing night lantern begins to fade. In its place emerges something far more remarkable. Not a symbol hanging above Earth, but a neighboring world drifting through darkness, carrying within its ancient stone the opening chapters of a story that ultimately includes our own. If the moon appears serene tonight, suspended above Earth like a silent lantern drifting through an ocean of darkness, it is easy to forget that its story may have begun in violence so immense that no natural disaster in human experience offers a meaningful comparison. The calm world we see now, traced in silver against the night sky, likely emerged from an event that unfolded when the solar system itself was still young, unstable, crowded, and unfinished, a time roughly 4.5 billion years ago, when planets were not yet the mature worlds we know today, but growing bodies assembling themselves from countless collisions among rocks, planetesimals, and embryonic worlds moving through a chaotic gravitational landscape. To understand why modern planetary scientists increasingly view the moon not as an object captured by Earth or born quietly beside it, but as the surviving consequence of a primordial catastrophe, it helps to imagine a solar system that looked nothing like the orderly arrangement we know now. During those early tens of millions of years, the region around the young sun contained enormous quantities of debris. Gravity was continuously gathering matter into larger structures, and every increase in size increased gravitational influence, which in turn attracted even more material. Growth therefore occurred through collision. Some impacts were gentle enough that objects merged. Others were energetic enough to shatter both participants. The architecture of the solar system emerged through this relentless process, a cosmic construction project powered by destruction. Within this environment, the young Earth was itself still evolving. It had not yet developed the stable continents, oceans, atmosphere, and biosphere that would characterize its later history. Instead, it was a partially molten planetary body, accumulating mass through repeated impacts. Somewhere within this dynamic environment, according to the leading giant impact hypothesis, another object may have existed, often referred to as Theia, a protoplanet perhaps comparable in size to Mars. The exact characteristics of this body remain uncertain because it no longer exists as a separate world, but numerical simulations suggest that a collision between Earth and a large planetary embryo could reproduce many of the features observed in the Earth-Moon system today. What makes this idea compelling is not merely its dramatic imagery, but the way it emerged from evidence rather than imagination. Earlier theories struggled to explain several fundamental observations. If the moon formed independently elsewhere and was later captured by Earth, the mathematics becomes problematic, because capture generally requires a mechanism to dissipate enormous amounts of orbital energy. If Earth and Moon form together from the same surrounding disk, it becomes difficult to explain certain differences in composition and angular momentum. If the Moon simply split away from a rapidly rotating Earth, questions arise regarding the rotational conditions necessary for such an event. None of these models fully satisfied the growing body of geological and dynamical evidence. The giant impact model gained traction because it addressed multiple constraints simultaneously. According to many versions of the scenario, Theia approached Earth on an intersecting orbit. The collision was likely not a direct head-on impact, but an oblique encounter, something closer to a glancing blow on a planetary scale. Yet the term glancing becomes almost meaningless when discussing bodies thousands of miles across, moving at velocities measured in kilometers per second. The kinetic energy involved would have exceeded anything imaginable in the modern world. Entire regions of both worlds may have vaporized. Vast quantities of molten rock and superheated material would have been ejected into space. The collision did not simply damage Earth, it fundamentally transformed it. In many simulations, a significant portion of the material thrown outward remained gravitationally bound to Earth, forming a rotating disk composed of molten droplets, rock fragments, vaporized silicates, and debris orbiting the planet. This structure is sometimes described as a debris disk, but that phrase can sound deceptively neat. In reality, it may have resembled a glowing ring of incandescent matter, extending tens of thousands of miles into space, radiating heat while orbiting a partially molten Earth beneath it. Within this disk, gravity once again became the architect. Small fragments collided and merged. Larger clumps attracted additional material. Over time, one dominant body emerged. That body would become the Moon. What is remarkable is that the physics governing this process are not fundamentally exotic. The same gravitational principles that cause dust grains in a protoplanetary disk to aggregate into planets can operate within a debris disk around a young Earth. The difference lies in scale, temperature, and timescale, rather than underlying physical law. This continuity is one of the elegant features of planetary science. The same equations describing orbital motion and gravitational attraction connect events separated by billions of years and millions of miles. Yet, as persuasive as the giant impact model became, the story did not end there. Science rarely settles into simplicity. One of the most intriguing developments emerged when scientists began analyzing lunar samples returned during the Apollo missions. Researchers expected the moon to contain a distinct chemical fingerprint if much of its material originated from another world. Instead, isotopic measurements revealed something surprising. Many lunar rocks appear extraordinarily similar to Earth rocks in certain isotopic ratios, including oxygen isotopes. This similarity was greater than some versions of the original giant impact model predicted. Rather than invalidating the impact hypothesis, these findings encouraged refinements. Perhaps the collision mixed material more thoroughly than earlier simulations suggested. Perhaps Theia itself formed in a region of the solar system compositionally similar to Earth. Perhaps the collision produced such extreme temperatures that large-scale homogenization occurred before the moon condensed from the resulting disk. Each possibility introduced new layers of complexity. In this way, the origin of the moon became not merely a solved mystery, but an evolving scientific conversation guided by increasingly precise evidence. Modern supercomputer simulations have added further depth to this discussion. Researchers now explore a wide range of impact conditions, varying mass ratios, impact angles, rotational velocities, and thermodynamic states. Some models propose multiple collisions rather than a single event. Others investigate structures known as synestias, enormous rotating masses of vaporized and molten material that may temporarily form after particularly energetic impacts. In these scenarios, the moon emerges not from a simple ring around Earth, but from a far more exotic transitional structure. These ideas remain subjects of active investigation, yet they demonstrate how scientific understanding grows. The goal is not to defend a single narrative, but to identify which models best match the evidence preserved in rocks, orbital dynamics, and planetary chemistry. Beneath all these technical details lies a deeper realization. The moon may represent a preserved fragment of a transformative moment in Earth's history. Without that collision, Earth itself would likely be different. Its rotation rate might have evolved differently. Its angular momentum budget would differ. The architecture of the Earth-Moon system as we know it might never have existed. In that sense, the moon is not merely something orbiting Earth. It may be part of Earth, material reshaped and reassembled through a process so energetic that the distinction between parent and offspring becomes almost philosophical. When viewed from this perspective, the moon begins to feel less like a neighboring object and more like a surviving memory. Every cratered plain, every mountain ridge, every field of ancient dust may ultimately trace its existence to a moment when two worlds met in darkness, and neither remained unchanged. Tonight, as moonlight drifts quietly across rooftops, forests, deserts, and oceans, there is no visible trace of that ancient collision. The sky reveals only the final result, not the unimaginable process that produced it. Yet hidden within the moon's rocks, within its orbit, within its chemical composition, and within the mathematical relationships that bind it to Earth, the evidence still remains. The tranquility we associate with the moon is therefore one of astronomy's most beautiful illusions. Beneath the appearance of permanence lies a history of chaos. Beneath the gentle glow lies the aftermath of planetary violence. And perhaps that contrast is part of what makes the moon so fascinating, because it reminds us that some of the most peaceful things in the universe were born from events almost beyond comprehension, their turbulent origins gradually fading into silence, until all that remains is a bright companion crossing the night sky, carrying within its ancient stone the memory of a world-shaping impact that occurred billions of years before the first ocean wave rolled onto a shore, or the first living cell stirred beneath Earth's sky. There is a tendency, when looking at the moon from Earth, to imagine that it has always been what it is now, cold, quiet, gray, and seemingly unchanged, a world so still that it appears almost outside of time itself. Yet the deeper planetary science investigates the earliest chapters of lunar history, the more that image dissolves into something startlingly different. Because there may have been a period when the moon was not a landscape of dust and craters at all, but a glowing sphere of molten rock, a world wrapped not in silence but in heat, where entire oceans existed not as water but as magma, stretching across vast portions of its surface. And understanding how such a transformation could occur requires us to follow the consequences of the immense impact discussed earlier, tracing the flow of energy through matter and allowing the laws of thermodynamics, gravity, and mineral physics to reveal what the newborn moon may have looked like during the first moments of its existence. If a large fraction of the moon formed from material ejected during a giant collision, then that material did not begin its journey as cool, solid stone. The energies involved in planetary scale impacts are so enormous that rock can melt, vaporize, and behave in ways that seem almost alien from the perspective of everyday experience. In human life, we encounter rock as something stable and permanent, but under sufficiently high temperatures and pressures, the distinction between solid, liquid, and vapor becomes far less intuitive. The debris surrounding the young Earth likely existed in a highly energetic state, and as gravitational attraction gradually assembled that material into a growing lunar body, additional heat would have been generated through accretion itself. Every collision between orbiting fragments converted kinetic energy into thermal energy. Every merger contributed to the warming of the growing moon. Radioactive isotopes present in the early solar system may also have provided supplementary heating. The result, according to many models, was not a cool sphere slowly forming in darkness, but a body whose outer layers, and perhaps much of its interior, became extensively molten. This idea, known as the lunar magma ocean hypothesis, has become one of the most influential frameworks in lunar geology, not because it emerged from speculation alone, but because it helps explain multiple observations that otherwise appear disconnected. The phrase magma ocean can be misleading if interpreted too literally. It does not necessarily imply waves of glowing lava visible across every horizon in exactly the way water covers Earth's oceans today. Rather, it describes a large-scale reservoir of molten silicate material occupying substantial portions of the moon's outer layers. In some models, this molten layer may have extended hundreds of kilometers deep. To appreciate the significance of such a state, it helps to imagine the moon not as a finished world, but as a planetary system undergoing differentiation, a process through which gravity gradually sorts materials according to density. Differentiation is one of the most fundamental mechanisms in planetary evolution. Whenever a sufficiently large body becomes molten, heavier materials tend to sink, while lighter materials tend to rise. The process is conceptually simple, yet produces extraordinary consequences. On Earth, differentiation contributed to the formation of the core, mantle, and crust. On the moon, a similar sorting process appears to have unfolded within the magma ocean itself. As the molten material slowly cooled, minerals began crystallizing. But minerals do not all crystallize at the same temperature, nor do they all possess the same density. Some formed earlier and sank deeper into the lunar interior. Others were less dense and accumulated closer to the surface. This gradual mineral segregation transformed a chaotic molten environment into an increasingly structured planetary body. One of the most important clues supporting this picture comes from a rock type known as anorthosite, which dominates much of the ancient lunar highlands. Anorthosite is rich in plagioclase feldspar, a mineral less dense than many surrounding materials. According to the magma ocean model, enormous quantities of plagioclase crystals formed as the molten moon cooled. Because these crystals were buoyant relative to the surrounding magma, they floated upward, accumulating into a primitive crust. In a sense, the earliest lunar crust may have formed like ice developing on the surface of a freezing lake, although the physics and materials involved were vastly different. This floating crust eventually solidified into the bright highland regions that still cover much of the moon today. What makes this idea especially compelling is that samples collected during the Apollo missions revealed extensive anorthositic material, precisely where the model predicted it should exist. Here, geology becomes a form of historical reconstruction. The rocks themselves function like surviving witnesses, preserving evidence of processes that occurred more than 4 billion years ago. Yet the cooling of the moon was not a simple march from liquid to solid. Planetary bodies possess thermal histories shaped by multiple interacting factors. Heat escaped into space through radiation. Crystallization altered internal dynamics. Residual radioactive decay continued generating energy. The growing crust acted as an insulating layer, affecting how efficiently deeper regions could cool. Even after substantial portions of the moon solidified, pockets of molten material may have remained beneath the surface for extended periods. This introduces an important realization. The moon's geological story was not defined by a single event, but by overlapping stages, each influencing the next. The magma ocean established chemical and structural conditions that shaped everything that followed. In this sense, understanding the molten moon is not merely understanding one chapter of lunar history. It is understanding the foundation upon which later chapters were built. As researchers developed increasingly sophisticated geochemical models, they discovered that the final stages of magma ocean crystallization may have concentrated certain incompatible elements into specific regions. Incompatible elements are those that do not easily fit into the crystal structures of common minerals, and therefore tend to remain in the residual liquid during crystallization. Over time, these elements become enriched within the remaining magma. Some lunar scientists refer to a geochemical component known as KREEP, named after elevated concentrations of potassium, rare earth elements, and phosphorus. Although invisible to casual observation, such compositional patterns provide important clues regarding how the lunar interior evolved. They suggest that the moon's early history involved not merely cooling, but increasingly complex chemical differentiation. What is particularly fascinating is how modern science arrives at these conclusions. No one can directly observe the ancient magma ocean. No telescope can look backward 4.5 billion years and watch it crystallize. Instead, scientists combine mineralogy, isotopic analysis, thermodynamic modeling, seismic data, orbital measurements, and laboratory experiments. Tiny variations in elemental abundance become pieces of a much larger puzzle. Equations describing phase transitions under specific temperature and pressure conditions become tools for reconstructing vanished environments. The result resembles forensic investigation conducted across planetary timescales. Every sample, every spectral measurement, every gravitational anomaly contributes another fragment to a story hidden beneath billions of years of history. Yet beyond the technical details lies an image that remains difficult to forget, once imagined clearly. There may have been a time when the moon glowed, not reflected sunlight, but its own heat radiating into space. A young Earth turning nearby may have illuminated the lunar sky with a presence far larger than the moon appears from Earth today. The distance between the two bodies was likely much smaller than it is now. The Earth itself may have still possessed extensive molten regions following the giant impact. In that ancient epoch, the Earth-Moon system would have looked less like the tranquil partnership we know, and more like a pair of evolving worlds emerging from catastrophe, both reshaped by extreme temperatures, both undergoing profound internal transformation. The moon's modern appearance can therefore be somewhat deceptive. Its cratered surface suggests permanence. Its stillness suggests completion. Yet the evidence preserved within its rocks points toward a youth defined by motion, heat, separation, crystallization, and chemical evolution. The bright highlands visible through telescopes are not merely terrain. They may be the fossilized surface of a planetary magma ocean. Their existence represents one of the earliest surviving geological records in the solar system. In a remarkable way, when we look at those ancient regions, we may be looking at material that formed while many of the processes shaping the planets were still underway. The moon becomes more than a companion world. It becomes an archive from a time when worlds themselves were still becoming worlds. And perhaps that is why the idea of a molten moon feels so compelling. It forces us to recognize that tranquility can emerge from turbulence, that structure can emerge from fluidity, and that the silent sphere drifting across our night sky carries within its ancient crust the memory of an age when it was neither gray, nor quiet, nor still, but a glowing ocean of stone suspended in darkness, slowly cooling beneath the laws of physics that continue to govern it even now. If you were to look at the full moon tonight with nothing more than your eyes, you would immediately notice a pattern that has fascinated humanity for thousands of years. Bright regions scattered across the lunar face, and vast, darker expanses that seem to form shapes, figures, and familiar markings. Ancient observers imagined rabbits, faces, trees, and mythological beings hidden within those shadows, while early astronomers, peering through primitive telescopes, arrived at an interpretation that felt entirely reasonable given what they knew at the time. The dark regions resembled oceans. They appeared smoother than the brighter surrounding terrain. They spread across enormous areas like inland seas viewed from a great distance, and so they were given names that remain with us today. Mare Imbrium, the Sea of Rains; Mare Tranquillitatis, the Sea of Tranquility; Mare Serenitatis, the Sea of Serenity. The names are beautiful, poetic, and strangely fitting for a world that dominates our night sky. Yet they conceal one of the most persistent visual illusions in planetary science, because these seas contain no water at all. They never contained oceans in the terrestrial sense. They are not dried lakebeds, ancient coastlines, or remnants of vanished lunar hydrology. They are something far more interesting. They are records of planetary violence preserved in stone, and understanding why they look the way they do requires us to follow a chain of events stretching back billions of years into the moon's earliest geological history. The first clue lies in a deceptively simple observation. The darker regions are not randomly distributed. Most of them are concentrated on the side of the moon facing Earth. This asymmetry immediately suggests that some large-scale geological process shaped the lunar surface differently across different regions. When spacecraft began mapping the moon in detail, scientists discovered that the dark areas are generally lower in elevation than the bright highlands surrounding them. They are broad plains rather than elevated plateaus. Their surfaces are smoother. Their crater densities differ. Their composition differs. Their history differs. What had once appeared from Earth as dark stains upon a pale sphere gradually emerged as an entirely separate geological province. To understand how these regions formed, it helps to imagine the moon after its magma ocean phase had largely ended. A crust had developed. Much of the surface had solidified, yet the solar system was still a dangerous place. During the first several 100 million years after planetary formation, enormous numbers of asteroids and leftover planetary building blocks continued moving through space. Collisions were not rare accidents. They were a normal feature of the environment. The moon, lacking a substantial atmosphere, possessed no protective shield against incoming objects. Every impactor struck directly. Every collision left a mark. Over time, some of these impacts became unimaginably large. Certain objects excavated basins hundreds of miles across. The energy released during such events exceeded anything humanity has ever witnessed. Entire sections of crust were shattered. Rock was melted and vaporized. Shock waves traveled through the lunar interior. Massive depressions formed where portions of the crust had been excavated or structurally weakened. Yet these impacts alone did not create the dark Maria. Instead, they prepared the stage for what came next. Beneath the moon's crust, residual heat and partially molten material still existed within portions of the interior. In regions where giant impacts had thinned the crust, pathways opened through which magma could eventually rise. Over immense spans of time, volcanic eruptions occurred, not as towering explosive mountains like those associated with some terrestrial volcanoes, but often as vast outpourings of basaltic lava. Because lunar gravity is weaker than Earth's, and because lunar magmas possessed particular physical properties, these eruptions could spread across enormous distances. Layer upon layer of dark basalt gradually flooded the giant impact basins. What we now call lunar seas are therefore immense volcanic plains. Their darkness arises largely from their composition. Basalt contains minerals richer in iron and magnesium than the feldspar-dominated rocks of the lunar highlands. These materials reflect less sunlight, producing the visual contrast visible even from Earth. The effect is subtle, yet profound. Human eyes interpret differences in brightness as differences in substance. We instinctively assert dark, smooth expanses with water, because water behaves similarly when viewed from a distance. The moon exploits that cognitive shortcut. It presents basalt and allows the brain to imagine oceans. In doing so, it reminds us that observation is only the beginning of understanding. Interpretation requires evidence. This distinction between appearance and reality appears repeatedly throughout astronomy. A galaxy may look compact, yet span hundreds of thousands of light years. A star may seem tiny while exceeding the size of Earth's orbit. The moon's Maria belong to the same tradition of cosmic misdirection. They are not evidence of what is present, but clues regarding what once happened. The more closely scientists examined these volcanic plains, the more information they revealed. Radiometric dating of lunar samples indicated that many Maria formed after the ancient highlands. This established a chronological sequence. First came crust formation following the magma ocean phase. Then came enormous basin-forming impacts. Then came volcanic flooding. The lunar surface therefore preserves a layered history rather than a single geological episode. Unlike Earth, where weather, oceans, erosion, plate tectonics, and biological activity continuously recycle the surface, the moon preserves evidence with remarkable fidelity. A crater created billions of years ago can remain recognizable today. Lava flows that solidified before complex life appeared on Earth can still be studied. In this sense, the moon functions almost like a geological archive. Every major terrain unit corresponds to a chapter of planetary history written directly into the landscape. Yet the Maria represent only one side of the story. The brighter highlands surrounding them tell another. These ancient terrains are heavily cratered, indicating extraordinary age. They preserve evidence of an era often referred to as heavy bombardment, when impacts occurred far more frequently than they do today. When viewed from orbit, the contrast between Maria and highlands becomes striking. The Maria appears smoother because younger volcanic activity partially buried older impact scars. The highlands appear rougher because they retain a more complete record of ancient bombardment. This difference allows planetary scientists to estimate relative ages through crater counting. The underlying logic is elegant. Surfaces exposed longer accumulate more impacts. Surfaces resurfaced by volcanic activity begin with a partially reset crater record. By analyzing crater densities statistically, researchers reconstruct sequences of events across billions of years. Mathematics becomes archaeology. Geometry becomes history. The moon transforms into a scientific narrative written in circles and shadows. Another fascinating aspect of the Maria involves their distribution. The side of the moon visible from Earth contains significantly more extensive Maria than the far side. This discrepancy remains an active area of research. One leading explanation suggests that the near side possessed a thinner crust in certain regions, allowing volcanic material to reach the surface more easily. Thermal evolution, radioactive element concentrations, impact history, and crustal structure may all have contributed. The important point is not that every detail has been solved, but that the pattern itself contains information. Planetary bodies are not random collections of rock. Their surfaces encode physical processes operating across immense scales of space and time. Even the fine dust covering the Maria contributes to the illusion. Over billions of years, countless micrometeorite impacts pulverized surface materials into a layer known as regolith. This blanket of fragmented rock covers much of the moon. Without atmosphere, wind, rain, rivers, glaciers, or biological activity, the primary agents of surface modification are impacts and thermal cycling. The result is a landscape unlike any naturally occurring environment on Earth. Silence dominates. Weather does not arrive. Water does not flow. Mountains do not erode in familiar ways. The passage of time expresses itself differently. Yet perhaps the most remarkable realization emerges when we step back and consider the entire sequence together. The dark seas that generations admired from Earth are not merely visual features. They are the frozen remains of ancient lava oceans that filled wounds created by colossal impacts. Their existence required planetary formation, crustal differentiation, basin excavation, internal heat retention, magma generation, volcanic flooding, and billions of years of preservation. A simple dark patch visible to the naked eye contains layer upon layer of geological history. The moon appears straightforward only because distance compresses complexity into a two-dimensional image. The closer science looks, the deeper the story becomes. What seemed to be water becomes stone. What seemed to be emptiness becomes evidence. What seemed to be decoration becomes documentation. And so the next time the full moon rises above the horizon, carrying its familiar pattern of bright and dark regions across the night sky, It may be worth remembering that those ancient seas are seas in name alone. They are not bodies of water reflecting moonlight. They are records of impacts, volcanism, chemistry, and planetary evolution, preserved with extraordinary patience across billions of years, waiting quietly in the darkness for anyone willing to look beyond appearance and discover the history hidden beneath the illusion. Among the many ideas people carry about the moon, few are as widespread and persistent as the phrase, the dark side of the moon. It appears in books, films, music, casual conversation, and even in the imagination of those who spend little time thinking about astronomy. The phrase feels intuitive. After all, if we always see the same face of the moon from Earth, then surely there must be another side permanently hidden in darkness. Yet one of the most fascinating lessons in planetary science begins with the realization that this familiar image is almost entirely wrong. The far side of the moon is not dark. It receives sunlight just as the near side does. It experiences day and night. It has sunrise and sunset. It spends roughly half of its time illuminated and half of its time in darkness, just as every rotating world exposed to the sun must. What makes the far side mysterious is not its relationship with sunlight, but its relationship with us. We do not see it from Earth, and the reason we do not see it leads directly into one of the most elegant examples of long-term gravitational physics in the solar system, a phenomenon known as tidal locking. At first glance, the moon appears to move across the sky with effortless simplicity. Night after night it rises, drifts overhead, and disappears beyond the horizon. Yet hidden beneath that familiar motion is a remarkable geometric relationship. The moon rotates on its axis. This surprises many people, because if the moon did not rotate at all, it would seem reasonable that we would always see the same side. In reality, the opposite is true. If the moon did not rotate while orbiting Earth, we would eventually see all of its sides over the course of a month. The fact that we continually face the same hemisphere means that the moon must rotate at exactly the right rate to keep one face directed toward Earth as it travels around its orbit. This relationship is not approximate. It is astonishingly precise. The moon completes one rotation relative to the distant stars in nearly the same amount of time that it completes one orbit around Earth, approximately 27.3 days. The result is a synchronization so complete that generations of humans, from ancient civilizations to the modern age, lived and died without ever seeing the far side directly. Understanding how this happened requires us to move beyond simple descriptions of motion and enter the deeper world of gravitational interactions. Gravity is often introduced as a force that pulls objects together, and while that description is useful, it captures only part of the story. Gravity also varies with distance. The side of the moon closest to Earth experiences a slightly stronger gravitational pull than the side facing away. This difference is small, yet over immense spans of time, even tiny forces can produce dramatic consequences. The unequal gravitational attraction creates what physicists call a tidal force. Although tides are often discussed in relation to oceans, tidal forces operate on solid bodies as well. Early in its history, the moon may have rotated much faster than it does today. If that were the case, Earth's gravity would have continuously attempted to align the moon's longest axis toward Earth. Any slight bulge in the moon's shape would experience torque, a rotational force capable of altering spin over time. The process was not sudden. It unfolded over millions of years, perhaps tens of millions. Internal friction converted rotational energy into heat. Gradually, the moon's spin slowed. Eventually, the system reached a stable configuration in which one rotation matched one orbit. At that point, tidal locking emerged. What is remarkable is that this outcome is not unique to the Earth-Moon system. Throughout the solar system, tidal locking appears repeatedly. Many moons orbiting giant planets exhibit similar behavior. Yet the Earth-Moon system offers perhaps the most familiar example because we witness its consequences every clear night. There is something quietly beautiful about this arrangement. The moon is not frozen by chance. It is participating in a gravitational dialogue billions of years old. The same force that governs planetary orbits also sculpted the rhythm of lunar rotation. Mathematics, in this context, becomes almost poetic. A small asymmetry in gravitational attraction, acting continuously across immense periods of time, reshaped the behavior of an entire world. Yet even after understanding tidal locking, another question naturally emerges. If we always see the same side, why does the moon sometimes appear to wobble slightly? Why do astronomers claim that over time, we can actually observe more than 50% of the lunar surface? The answer introduces another subtle layer of orbital geometry known as libration. The moon's orbit is not a perfect circle. Its orbital speed changes slightly as it moves closer to and farther from Earth. Meanwhile, its rotational speed remains comparatively steady. This mismatch produces an apparent rocking motion. Additional effects arise from the inclination of the moon's rotational axis and the perspective changes caused by Earth's own rotation. Combined, these factors allow observers to glimpse around the edges of the lunar globe. Over time, approximately 59% of the lunar surface becomes visible from Earth, though never all at once. Libration is a reminder that celestial mechanics often resist simple categories. The moon is neither completely revealing nor completely hidden. It exists in a state of partial disclosure, offering slightly different views while preserving its deepest geographical secrecy. For centuries, the far side remained inaccessible, not because it was physically unreachable, but because geometry prevented direct observation. Even the most powerful telescopes on Earth could not solve this problem. No improvement in magnification could reveal terrain permanently turned away from us. Only the arrival of spaceflight changed the situation. In October of 1959, the Soviet spacecraft Luna 3 achieved something extraordinary. As it passed around the moon, it photographed the far side and transmitted the images back to Earth. The photographs were primitive by modern standards, yet their impact was profound. Humanity saw the hidden hemisphere for the first time. What appeared was not what many expected. The far side looked dramatically different from the familiar near side. The vast, dark maria that dominate the face visible from Earth were largely absent. Instead, the far side was heavily cratered and covered by rugged highlands. This asymmetry immediately became a scientific puzzle. Why should two hemispheres of the same world differ so dramatically? Over subsequent decades, increasingly sophisticated missions gathered data that gradually revealed part of the answer. The lunar crust on the far side appears, on average, thicker than the crust on the near side. A thicker crust may have made it more difficult for basaltic magma to reach the surface after giant impacts created deep basins. Consequently, fewer maria formed. The familiar dark seas visible from Earth therefore represent not a universal lunar feature, but a regional geological phenomenon. Once again, the moon demonstrated its ability to deceive casual observation. The side we know best is not representative of the entire world. It is merely one hemisphere shaped by a particular geological history. This realization carries a deeper philosophical resonance. Human beings naturally mistake familiarity for completeness. We assume that repeated observation produces comprehensive understanding. Yet, the moon teaches the opposite lesson. For thousands of years, we observed it constantly while remaining ignorant of nearly half its surface. The hidden hemisphere existed all along, silently orbiting above every civilization that ever gazed upward. Its mountains, basins, and craters were real long before they were known. Knowledge did not create them. Discovery merely expanded awareness. Modern lunar exploration continues to build upon this theme. Orbiters have mapped the far side in extraordinary detail. Landers have successfully reached regions once considered inaccessible. Scientists study differences in crustal thickness, impact history, thermal evolution, and geochemistry across both hemispheres. Every dataset reveals new complexities. Every measurement reminds us that even the nearest celestial body remains richer and more intricate than first impressions suggest. Yet, perhaps the most fascinating aspect of tidal locking is that it transforms what appears to be a static relationship into evidence of dynamic history. The moon is not showing us the same face because nothing happens. It is showing us the same face because countless interactions happened. Gravitational forces, rotational energy, internal friction, orbital evolution, and geological structure all contributed to the configuration we see today. Stability itself became the final product of change. The quiet moon hanging above Earth is therefore not a symbol of stillness, but the result of billions of years of motion gradually settling into balance. And so the next time moonlight spills across a landscape and the familiar lunar face rises above the horizon, it may be worth remembering that there is no dark side permanently hidden from the sun. There is only a far side, illuminated by the same sunlight, shaped by the same cosmic history, and bound to Earth through a gravitational partnership so precise that it has preserved the same view for all of recorded human history, a silent demonstration that even in the apparent stillness of the night sky, profound physics is always at work. Stand beside the ocean late at night, when the wind has softened and the world seems to be speaking in whispers rather than voices, and you may notice something curious about the sea. It never truly rests. Even on the calmest evening, when the surface appears almost motionless beneath the glow of moonlight, the water is participating in a rhythm far larger than itself, a slow planetary pulse that has been repeating for billions of years. Long before human beings built ports, charted coastlines, launched ships, or even existed as a species, the oceans were already rising and falling in response to an invisible conversation between Earth and the Moon. This conversation is so familiar that it often escapes notice. We learn that the Moon causes tides and feel satisfied with the explanation. Yet that simple statement conceals one of the most elegant and misunderstood phenomena in celestial mechanics. The Moon does not pull the oceans upward in the way a magnet attracts metal. It does not lift a giant mound of water directly beneath itself while leaving the rest of Earth unchanged. The actual physics is more subtle, more beautiful, and in many ways, more surprising. To understand it, we must first step away from the shoreline and imagine Earth from space, not as a map or a globe, but as a dynamic physical system immersed within a constantly changing gravitational field. Gravity weakens with distance. This simple principle, described mathematically through Newton's law of gravitation, becomes the foundation of the entire tidal phenomenon. The side of Earth facing the Moon is slightly closer to the Moon than Earth's center. Earth's center is slightly closer than the far side. These differences may seem insignificant on human scales, yet across the diameter of a planet, they become measurable. Because gravitational attraction decreases with distance, the near side experiences a slightly stronger pull than the center, while the far side experiences a slightly weaker pull. This difference, rather than gravity itself, generates tides. Physicists call this a tidal force, and it represents one of the most important concepts in planetary dynamics. If gravity were identical across the entire Earth, no tides would exist. The oceans respond not to gravity alone, but to variations in gravity. The result is something remarkably elegant. Water on the side facing the Moon is pulled slightly more strongly toward the Moon than the solid Earth beneath it, creating a tidal bulge. At the same time, water on the opposite side experiences a weaker lunar pull than Earth's center, causing the planet itself to move slightly more toward the Moon than the far side water does. Relative to Earth, this creates a second bulge on the opposite side. The existence of two tidal bulges often surprises people because intuition suggests there should be only one. Yet the mathematics reveals otherwise. Earth rotates through these bulges, causing most coastlines to experience two high tides and two low tides during roughly each lunar day. Already the picture becomes richer than the simplified diagrams often presented in textbooks. Yet the oceans do not behave like a perfectly smooth shell of water covering a perfectly spherical planet. Earth is neither perfectly spherical nor uniformly covered by ocean. Continents interrupt the movement of water. Ocean basins possess different depths and shapes. The seafloor redirects energy. Coastlines amplify or dampen tidal motion. Coriolis effects arising from Earth's rotation further complicate the system. As a result, real tides are far more complex than the idealized tidal bulges described in introductory models. In certain locations, tidal ranges may measure only a few inches. In others, such as Canada's Bay of Fundy, tidal differences can exceed 50 feet. The same gravitational forcing interacts with vastly different local conditions, producing dramatically different outcomes. This reveals a recurring theme throughout planetary science. Simple physical laws often generate astonishing complexity when applied within real environments. The Moon's gravitational influence may be global, but its expression is profoundly local. Every harbor, estuary, bay, and coastline translates the universal language of gravity into its own unique pattern. Yet the story becomes even more fascinating when we recognize that the oceans are not the only things responding to lunar tides. Earth itself is flexible. Although it feels rigid beneath our feet, the planet is not an immovable object. The same tidal forces affecting the oceans also deform the solid Earth. The crust rises and falls by measurable amounts as the moon passes overhead. These movements are much smaller than ocean tides, yet modern instruments can detect them with extraordinary precision. The ground beneath us participates in the same gravitational rhythm as the sea. Mountains, deserts, forests, cities, and plains all experience subtle tidal distortions. The Earth breathes, not metaphorically, but physically. Even the atmosphere responds. Atmospheric tides exist as well, driven by both gravitational effects and solar heating. The deeper one looks, the more the Earth-Moon system begins to resemble a continuously interacting, dynamical structure rather than two separate worlds. Nothing remains entirely unaffected. The influence of the moon reaches into water, rock, and air alike. Historically, humanity recognized tidal cycles long before understanding their cause. Ancient civilizations observed predictable changes along coastlines and incorporated them into navigation, fishing, commerce, and calendars. Yet the underlying mechanism remained mysterious. Some explanations linked tides to winds, others invoked hidden forces or celestial harmonies. The transition from observation to scientific understanding unfolded gradually. As mathematics, astronomy, and physics matured, tides became one of the earliest phenomena demonstrating the predictive power of gravitational theory. When Newton proposed universal gravitation in the 17th century, tides provided powerful supporting evidence. The same force causing an apple to fall could also explain the movement of oceans and the motion of the moon itself. Suddenly, phenomena occurring on vastly different scales became unified within a single conceptual framework. A wave touching a shoreline and a celestial body orbiting through space could be described using related physical principles. This intellectual achievement transformed not only astronomy, but humanity's understanding of nature itself. Yet even Newton's framework represented only part of the story. Modern geophysics and oceanography reveal additional layers of complexity, involving resonance, fluid dynamics, rotational effects, and nonlinear interactions. Certain ocean basins possess natural oscillation frequencies that can amplify tides. Energy transferred through tidal motion dissipates as heat due to friction between moving water and the seafloor. This friction may seem minor, yet over immense timescales it produces consequences reaching far beyond the shoreline. One of the most remarkable outcomes is that tides gradually alter Earth's rotation. Every tidal cycle involves the transfer and dissipation of energy. The tidal bulges do not remain perfectly aligned beneath the moon because Earth rotates more quickly than the moon orbits. As a result, the bulges are carried slightly ahead of the Earth-Moon line. This offset creates a gravitational interaction that transfers angular momentum from Earth to the moon. The process is extraordinarily slow, invisible within a human lifetime, yet measurable with modern technology. Laser reflectors placed on the moon by Apollo astronauts allow scientists to determine the Earth-Moon distance with astonishing precision. Measurements indicate that the moon is slowly moving away from Earth by approximately 3.8 centimeters per year. At the same time, Earth's rotation is gradually slowing. Days are becoming longer, though the change is measured in milliseconds per century. Here the tides reveal their deepest significance. They are not merely motions of water. They are mechanisms through which energy and angular momentum move between worlds. Every wave participating in the tidal cycle contributes, however slightly, to a planetary evolution unfolding across billions of years. The moon influences the oceans, and the oceans influence the future trajectory of the Earth-Moon system. The relationship is reciprocal rather than one-sided. There is something quietly profound about this realization. When standing beside the sea, it is easy to think of the ocean as a local feature and the moon as a distant object. In reality, they are components of a single gravitational system. The water rising along a shoreline is responding to a body nearly 250,000 miles away. The mathematics connecting them remains invisible, yet the effects are tangible. Every high tide becomes evidence that distance does not imply separation. The Earth and Moon remain linked through physical laws operating continuously across space. And perhaps that is what makes tides so captivating when viewed through the lens of planetary science. They transform gravity from an abstract equation into a living phenomenon. They reveal that celestial mechanics is not confined to observatories, spacecraft, or distant stars. It unfolds twice each day along every coastline on Earth. The Moon, hanging silently above the horizon, is not merely a companion world. It is an active participant in the rhythm of our planet, gently pulling upon oceans, subtly flexing the crust, slowly reshaping orbital dynamics, and maintaining a gravitational conversation that began billions of years ago and continues tonight beneath the quiet glow of moonlight reflected across the restless surface of the sea. Imagine Earth viewed not from the surface, where seasons arrive gradually and familiarity disguises their deeper origins, but from far beyond the orbit of the Moon, where our planet appears as a rotating blue sphere, tilted slightly as it circles the Sun, carrying oceans, continents, clouds, and every living thing through space. From that distant perspective, one of the most important facts about Earth becomes immediately visible. Our planet does not spin upright. Its rotational axis is tilted by approximately 23.5 degrees relative to the plane of its orbit around the Sun. That tilt is responsible for the changing seasons, for the shifting length of days and nights, for the migration of climate zones across the calendar year, and for countless environmental rhythms that have shaped the history of life. Yet hidden behind this familiar fact lies a deeper question, one that leads us into one of the most fascinating and subtle relationships in planetary science. Why is Earth's tilt relatively stable over long periods of time? Why has our world avoided the extreme axial chaos seen elsewhere in the solar system? And to what extent has the Moon quietly participated in maintaining that stability for billions of years? At first glance, the question may seem surprisingly abstract. The Moon is often associated with tides, moonlight, and eclipses. Climate appears to belong to an entirely different category of phenomena. Yet when scientists began examining the long-term dynamics of planetary rotation, they discovered that the connection between the Moon and Earth's climatic history may be far more profound than earlier generations imagined. To understand why, we must first think of Earth not as a static object, but as a rotating body subject to continuous gravitational influences. Every spinning object possesses angular momentum, a property that resists changes in orientation. A spinning top provides a useful analogy. While rotating rapidly, it tends to maintain its axis in a particular direction. External forces can alter that orientation, but they do so gradually. Earth behaves in a similar way. The planet spins once every 24 hours, generating substantial angular momentum. However, Earth is not a perfect sphere. Rotation causes a slight equatorial bulge, making the planet wider around the equator than from pole to pole. This asymmetry creates an opportunity for external gravitational forces to exert torque on the planet. The Sun contributes such torques. The Moon contributes them as well. Together, they influence the long-term behavior of Earth's rotational axis. Yet the story becomes more interesting when we recognize that an axis does not simply point in one direction forever. Like a spinning top, Earth's axis undergoes a slow motion known as precession. Over approximately 26,000 years, the direction of the axis traces a broad circle through space. The North Star of today will not remain the North Star forever. Thousands of years from now, different stars will occupy that position. Precession itself is not unusual. Many rotating bodies experience similar behavior. What matters is the rate at which it occurs, and how that rate interacts with other gravitational cycles operating throughout the solar system. Here the Moon enters the story in a subtle but potentially crucial way. Because the Moon is unusually large relative to Earth compared with most planetary satellite systems, its gravitational influence on Earth's equatorial bulge is substantial. This influence increases the precession rate of Earth's axis. At first, this may sound like a minor technical detail, yet within celestial mechanics, small differences in frequency can determine whether a system remains relatively stable or enters regimes of stronger dynamical variation. Planetary scientists often study these questions through mathematical models describing resonances. Resonance occurs when different cycles interact in ways that amplify motion. A familiar example appears when a singer shatters a glass by matching its natural frequency. In orbital dynamics, resonances can gradually magnify changes over immense timescales. If Earth's axial precession frequency aligned more closely with certain gravitational frequencies generated by the planets, larger variations in obliquity, the angle of Earth's tilt, might become possible. The presence of the Moon alters this dynamical landscape. It shifts the system away from some potentially destabilizing resonant interactions. This realization emerged gradually through increasingly sophisticated numerical simulations. Researchers began asking a remarkable question. What would happen if Earth had no large moon? The answers varied depending on model assumptions, reflecting the complexity of the problem, but many simulations suggested that Earth's obliquity could experience significantly larger variations over geological timescales. Rather than oscillating within relatively moderate bounds, the tilt might wander more dramatically. Some scenarios produced swings capable of substantially altering climate patterns. It is important to emphasize that these results do not imply certainty. Planetary dynamics involves many interacting variables, and the exact history of a moonless Earth remains unknowable. Yet the possibility itself is striking. The Moon may function not merely as a companion world, but as a stabilizing influence within Earth's rotational architecture. The comparison with Mars provides an intriguing perspective. Mars lacks a large, stabilizing moon. Its two small moons, Phobos and Deimos, are tiny compared with our moon and contribute little to axial stabilization. Studies suggest that Mars has experienced substantial obliquity variations throughout its history. At certain times, its tilt may have differed dramatically from its present value. Such changes influence the distribution of sunlight across the planet, affecting ice deposits, atmospheric circulation, and long-term climate evolution. While Mars and Earth differ in many ways, the comparison highlights how rotational dynamics can shape planetary environments. It suggests that the geometry of a planet's spin may matter almost as much as its distance from the Sun. The implications become even more interesting when viewed through the lens of habitability. Climate stability does not mean climate uniformity. Earth has experienced ice ages, warming periods, shifting ecosystems, and dramatic environmental transformations. Geological records reveal a dynamic world rather than a static one. Yet these changes occurred within a framework that remained broadly compatible with the persistence and evolution of complex life. The Moon did not create life, and scientists generally avoid claiming that a large moon is a universal requirement for habitability. Many potentially habitable worlds may exist without one. Nevertheless, Earth's particular evolutionary history unfolded within a system where the Moon may have contributed to maintaining long-term rotational stability. That possibility invites a fascinating shift in perspective. The Moon's influence extends beyond visible tides and moonlit nights into the deeper architecture of planetary behavior. Climate itself becomes linked, however indirectly, to celestial mechanics. The changing seasons we experience each year are ultimately consequences of geometry. Geometry becomes climate. Climate becomes ecology. Ecology becomes part of the context within which evolution unfolds. Following this chain of relationships reveals how interconnected planetary systems truly are. Nothing exists in isolation. The angle of a spinning planet influences the distribution of sunlight. The distribution of sunlight influences atmospheric circulation. Atmospheric circulation influences ecosystems. Ecosystems influence evolutionary pathways. Somewhere near the beginning of that sequence stands a large natural satellite orbiting hundreds of thousands of miles away. Another fascinating aspect of this story is that the Moon's stabilizing role may itself be a consequence of the giant impact that likely formed it. The same collision that reshaped the early Earth may have created the very object that later influenced Earth's rotational behavior. In that sense, the history of the Earth-Moon system contains a remarkable continuity. A violent event in the distant past may have established conditions that quietly affected the planet's future for billions of years. Chaos gave rise to structure. Catastrophe contributed to stability. Such patterns appear repeatedly throughout planetary evolution. Systems that seem calm today often emerge from periods of extraordinary turbulence. Yet perhaps the most beautiful aspect of this entire discussion is how invisible it remains in everyday life. No one watching a sunset can directly see the moon stabilizing Earth's rotational dynamics. No one walking through autumn leaves senses precession frequencies or gravitational torques. The effects reveal themselves only through mathematics, simulation, observation, and patient scientific inquiry. And yet, they are real possibilities embedded within the machinery of the solar system. The moon, hanging above the horizon, appears silent, detached from the concerns of climate and life below. But appearances, as we have repeatedly discovered throughout this journey, can be deceptive. Beneath that calm silver presence lies a gravitational relationship woven deeply into the history of our planet. Whether viewed through equations describing rotational dynamics or through the broader story of Earth's environmental evolution, the moon emerges not merely as a passive companion, but as a quiet participant in the long-term stability of the world we call home. A distant guardian whose influence is measured not in days or years, but across the immense, slow-moving rhythms of planetary time. On a clear night, the moon appears eternal. It rises where generations before us watched it rise, follows a familiar path across the sky, and settles beyond the horizon with such dependable regularity that it feels almost permanent, as though the Earth and moon were locked together in an arrangement that has always existed and always will. Yet one of the most remarkable discoveries in modern planetary science is that this apparent permanence conceals a slow and ongoing separation. The moon is not maintaining a fixed distance from Earth. It is moving away, very slowly, almost imperceptibly from the perspective of a human life, yet continuously. Every year, the average distance between Earth and the moon increases by approximately 3.8 centimeters, roughly the rate at which fingernails grow. At first, this number seems trivial. A few centimeters scattered across nearly 400,000 kilometers appears insignificant. But planetary history is written not in years or centuries, but in millions and billions of years. And when small changes operate continuously across such immense spans of time, they reshape worlds. The realization that the moon is gradually receding from Earth transforms our understanding of the Earth-Moon system. It reveals that what appears stable is actually evolving, and that tides are not merely daily movements of water, but manifestations of a deeper exchange involving energy, momentum, and time itself. To understand why the moon is moving away, we must return to the tidal interaction between Earth and its companion. Earlier, we explored how the moon raises tidal bulges in Earth's oceans through differential gravity. But those tidal bulges are not perfectly aligned beneath the moon. Earth rotates much faster than the moon orbits. A day lasts approximately 24 hours, while the moon requires more than 27 days to complete a sidereal orbit. Because Earth spins so rapidly, the tidal bulges are carried slightly ahead of the Earth-Moon line. Imagine a rotating sphere wrapped in moving oceans. As Earth turns, friction between ocean water and the seafloor drags the tidal bulges forward. The result is a subtle but crucial geometric offset. The bulges no longer point directly toward the moon. Instead, they lead it slightly. This small angular displacement changes everything. The mass, concentrated within those displaced bulges, exerts its own gravitational pull on the moon. Because the bulges are positioned slightly ahead of the moon in its orbit, their gravity pulls the moon forward rather than directly inward. A forward pull increases orbital energy. According to the laws of orbital mechanics, when an orbiting body gains energy in this manner, it moves into a larger orbit. Consequently, the moon gradually drifts farther away from Earth. This process is elegant because it demonstrates a fundamental principle of physics. Energy is not appearing from nowhere. It is being transferred. The source of that energy is Earth's rotation. As the moon gains orbital energy and angular momentum, Earth loses rotational energy. The planet spins slightly more slowly. Days become marginally longer. The moon moves marginally farther away. The system evolves while conserving angular momentum. In a sense, Earth is paying for the moon's outward migration with its own rotational speed. What makes this phenomenon extraordinary is that it can be measured directly. During the Apollo missions, astronauts placed retroreflectors on the lunar surface. These devices function like extraordinarily precise mirrors. Scientists on Earth can fire laser pulses toward them and measure the time required for the light to return. Because light travels at a known speed, the distance can be calculated with remarkable accuracy. Decades of measurements reveal that the moon is indeed receding at approximately 3.8 centimeters per year. This is not speculation. It is one of the most precisely measured motions in planetary science. Yet the modern recession rate tells only part of the story. Geological evidence suggests that the Earth-Moon system looked dramatically different in the distant past. Hundreds of millions of years ago, Earth rotated more rapidly than it does today. Fossil growth patterns preserved in ancient corals and shell-forming organisms provide surprising clues. Certain organisms record daily and annual growth cycles within their structures. By counting these patterns, scientists can estimate the number of days that occurred within a year at different points in Earth's history. The results suggest that hundreds of millions of years ago, a year contained more days because each day was shorter. During the Devonian period, approximately 400 million years ago, a day may have lasted around 22 hours. Going even farther back, the differences become more pronounced. This evidence aligns beautifully with the tidal evolution model. As Earth's rotation slows, the length of the day increases. The fossil record and celestial mechanics tell the same story from entirely different directions. One begins with ancient organisms. The other begins with gravitational equations. Both converge on the same conclusion. The Earth-Moon system has been changing continuously. If we continue traveling backward through time, the picture becomes even more dramatic. Shortly after its formation, the Moon may have orbited far closer to Earth than it does today. Some models suggest that the young Moon could have appeared enormous in the sky, occupying many times the angular diameter familiar to modern observers. The tides generated by such a nearby moon would have been vastly stronger. Coastal environments, if oceans existed in comparable forms during those periods, would have experienced tidal conditions difficult to imagine today. The Earth itself would have rotated much faster. A day lasting only a few hours may have characterized certain early phases of planetary evolution. The Earth-Moon system we know now is therefore not the original configuration. It is merely the current frame in a continuously unfolding process. This realization introduces a profound perspective on time. Human beings naturally think in scales of decades. Civilizations think in centuries. Geological systems think in millions of years. Planetary systems think in billions. Against that backdrop, the Moon's recession becomes visible not as a minor detail, but as a major chapter in the long-term evolution of Earth. Every tide participates in that chapter. Every movement of water contributes, however slightly, to the transfer of energy that gradually reshapes the architecture of the system. Yet the future of this process is equally fascinating. What happens if the Moon continues moving away indefinitely? The answer reveals the limits of intuition. Although the Moon is receding, it will not simply drift off into deep space. The Earth-Moon system remains gravitationally bound. Instead, if no other influences intervened, tidal evolution would gradually push the system toward a state of mutual synchronization. Earth's rotation would continue slowing, while the Moon's orbital distance increased. Eventually, a theoretical equilibrium could emerge in which Earth's rotation period matched the Moon's orbital period. Just as the Moon currently shows the same face to Earth due to tidal locking, Earth would eventually show the same face to the Moon. Both worlds would become mutually locked. One hemisphere of Earth would always face the Moon, while the opposite hemisphere would never see it. Yet this outcome lies so far in the future that other astrophysical processes will likely intervene long before it can be fully realized. The Sun itself is evolving. Billions of years from now, solar changes will dominate the destiny of Earth. Tidal evolution unfolds slowly, but stellar evolution unfolds inexorably. The future of the Earth-Moon system therefore exists within an even larger cosmic context. Another intriguing aspect of lunar recession is how it demonstrates the interconnectedness of physical systems. The Moon influences Earth's tides. Tides influence Earth's rotation. Earth's rotation influences the Moon's orbit. The Moon's orbit influences future tidal behavior. Each component affects the others. No element can be understood entirely in isolation. This interconnected structure resembles a conversation rather than a collection of separate mechanisms. Gravity speaks through motion. Motion alters geometry. Geometry modifies future interactions. The system continually rewrites itself according to the same underlying laws. There is something quietly poetic about this. The moon often appears detached from Earth, suspended in the darkness like an independent traveler. Yet the physics tells a different story. Earth and moon remain engaged in an ancient exchange. Every high tide, every low tide, every subtle deformation of ocean and crust contributes to a transfer of momentum that has persisted for billions of years. The moon's outward journey is not a departure caused by separation. It is a consequence of connection. The stronger the gravitational relationship, the more effectively energy is exchanged. The recession exists because the bond exists. And perhaps that is the deepest lesson hidden within this slow celestial migration. The moon is moving away, but not because the relationship is weakening. It is moving away because gravity has linked the two worlds so intimately that neither can evolve without influencing the other. The tides rolling across Earth's oceans tonight are not merely movements of water beneath moonlight. They are visible expressions of a planetary scale transaction that began in the earliest history of the solar system and continues even now, silently transferring energy across space, lengthening our days, expanding the moon's orbit, and reminding us that even the most familiar objects in the night sky are participants in stories far larger, older, and more dynamic than they first appear. When people imagine the moon, they often picture a destination that humanity visited, planted flags upon, collected a few rocks from, and then largely left behind. A place whose greatest mysteries were solved decades ago during the Apollo era. Yet, among planetary scientists, geologists, astronomers, and astrobiologists, a very different perception has emerged over the last several decades. The moon is increasingly viewed not as a completed chapter in the history of exploration, but as one of the most valuable scientific archives in the entire solar system. A place where events that occurred billions of years ago remain preserved with a clarity that Earth itself can no longer provide. This is one of the reasons scientists continue advocating for new lunar missions, not simply because returning to the moon represents a technological achievement, but because the moon contains information that may help answer some of the deepest questions humanity can ask about planetary formation, the history of Earth, the evolution of the solar system, and perhaps even the conditions that eventually made life possible. To understand why the moon functions as such an extraordinary archive, it helps to begin with a comparison. Earth is a dynamic world. Mountains rise and erode. Oceans reshape coastlines. Rivers transport sediment. Winds sculpt landscapes. Volcanoes create new surfaces. Plate tectonics recycles vast portions of the crust. Biological activity transforms the environment continuously. These processes make Earth vibrant and habitable, yet they also destroy evidence. Geological records become fragmented, ancient surfaces disappear. Traces of the earliest epochs of planetary history are often buried, altered, or erased entirely. In contrast, the moon lacks nearly all of these mechanisms. It possesses no global atmosphere capable of generating weather. It has no active oceans. It lacks Earth-like plate tectonics. Its surface has remained comparatively stable for immense spans of time. As a result, features that formed billions of years ago can still be observed today. In a very real sense, the moon remembers what Earth has forgotten. This difference becomes especially important when considering the earliest history of the solar system. Approximately 4.5 billion years ago, the planets were forming within a chaotic environment, filled with collisions, migrating bodies, and leftover debris from planetary construction. Many of the events that shaped Earth during that period left little surviving evidence because subsequent geological activity erased much of the record. The moon, however, preserves numerous clues. Ancient impact basins, primordial crustal materials, and some of the oldest exposed surfaces known in the solar system remain accessible for study. When scientists examine these regions, they are not merely investigating lunar history, they are studying conditions that existed when Earth itself was still becoming Earth. The moon, therefore, acts as a time capsule, preserving information from an era that would otherwise remain largely inaccessible. One of the most transformative moments in this scientific effort occurred during the Apollo missions. Although Apollo is often remembered primarily as an engineering triumph, its scientific legacy may ultimately prove even more significant. Astronauts returned hundreds of kilograms of lunar material to Earth. These samples became some of the most valuable geological specimens ever collected. Laboratory analysis revealed ages extending back more than 4 billion years. Isotopic measurements provided clues regarding the moon's formation. Mineral compositions illuminated the history of the lunar magma ocean. Impact melt rocks helped reconstruct periods of intense bombardment. Decades after their collection, Apollo samples continue generating new scientific discoveries because advances in analytical technology allow researchers to extract information that was impossible to detect when the rocks first arrived on Earth. Every improvement in instrumentation effectively creates a new opportunity to ask questions of old samples. Yet despite the immense value of Apollo's collections, they represent only a tiny fraction of the moon. Most samples came from a limited number of locations concentrated on the near side. Vast regions remain unexplored. The far side, polar regions, deep basins, and numerous geologically distinct terrains have never been sampled directly by humans. This is one reason scientists continue advocating for additional exploration. The moon's archive remains largely unread. We possess fragments of the story rather than the entire narrative. Another compelling reason for returning involves the history of impacts throughout the inner solar system. Craters cover the lunar surface in astonishing numbers. Each crater represents an event. Each event contains information. By determining the ages of impact structures and understanding their distribution, researchers hope to reconstruct the bombardment history of the early solar system. Some models suggest periods of elevated impact activity. Others propose more gradual decline patterns. The precise timeline remains an active area of research. Resolving these questions matters because impacts influence the evolution of all terrestrial planets, including Earth. Understanding when major impacts occurred may help clarify the environmental conditions under which early life emerged and evolved. Once again, the moon serves as a proxy record for processes affecting worlds far beyond itself. Yet the scientific importance of the moon extends beyond ancient rocks and impact histories. One of the most exciting modern discoveries involves water ice. For much of the 20th century, the moon was commonly described as completely dry. That description now appears oversimplified. Orbital measurements, impact experiments, and remote sensing data have revealed evidence for water ice in permanently shadowed regions near the lunar poles. These locations are particularly fascinating because their interiors may never receive direct sunlight. Temperatures remain extraordinarily low. Molecules delivered by comets, asteroids, solar wind interactions, or internal geological processes may accumulate and remain preserved for immense periods of time. In effect, some polar craters may function like cold storage vaults, preserving records of volatile materials from different phases of solar system history. Studying these deposits could reveal valuable information about the movement of water and other compounds throughout the inner solar system. The implications extend even further. Water is not merely scientifically interesting, it is also operationally important. Future exploration efforts may use lunar ice as a resource. Water can support human life. It can be separated into hydrogen and oxygen. These elements can serve as rocket propellant. Thus, a scientific discovery simultaneously becomes a practical consideration for long-term exploration. This intersection between science and exploration represents one of the defining characteristics of modern lunar research. The moon is not only a subject of investigation, it may also become a platform for future investigations extending deeper into space. The renewed interest in lunar exploration through programs such as Artemis reflects this broader vision. The objective is not simply to repeat Apollo. Apollo demonstrated that humans could reach the moon. Modern efforts aim to establish sustained scientific presence, develop new technologies, investigate previously unexplored regions, and create infrastructure supporting future missions. Scientists are particularly interested in the lunar South Pole because of its unique illumination conditions, potential ice deposits, and scientific opportunities. Every new mission has the potential to transform our understanding of planetary evolution. There is also another, often overlooked reason why researchers value the moon so highly. It offers a laboratory for studying processes that operate throughout the solar system. impact cratering, regolith formation, space weathering, volcanic history, crustal evolution, and thermal development are not uniquely lunar phenomena. They occur on other worlds as well. The moon provides an accessible environment where these processes can be investigated in detail. Knowledge gained there can improve interpretations of observations collected from Mercury, Mars, asteroids, and distant planetary satellites. In this sense, lunar science extends far beyond the moon itself. It becomes a framework for understanding planetary systems more generally. Perhaps the most profound aspect of the moon's scientific value, however, lies in the perspective it offers on time. Human history occupies only a tiny fraction of the timescales recorded in lunar rocks. Civilizations rise and fall within intervals that barely register geologically. Yet the moon preserves evidence stretching back almost to the beginning of the solar system. Holding a lunar sample is, in a sense, holding a fragment of deep time itself. The rock becomes more than material. It becomes a witness. It existed before continents took their modern shapes, before complex life appeared, before forests, dinosaurs, mammals, or humans. Few objects available for direct study possess such historical depth. And perhaps that is why scientists continue wanting to return. Not because the moon is familiar, but because it remains profoundly unfamiliar. Not because we have learned everything from it, but because we have only begun. Beneath its quiet surface lies a record spanning nearly 4.5 billion years, a geological archive written in minerals, isotopes, impact scars, volcanic plains, and frozen deposits hidden within permanent darkness. Every unanswered question points toward another layer of that archive waiting to be explored. Every future mission becomes an opportunity to read another page. And as the moon drifts silently above Earth tonight, appearing unchanged to casual observation, it continues to carry within its ancient rocks one of the most complete surviving records of our cosmic origins, patiently preserving a story that scientists are still learning how to read. After traveling through billions of years of planetary history, through molten oceans of rock, colossal impacts, hidden hemispheres, migrating orbits, gravitational tides, and the delicate architecture of celestial mechanics, we arrive at a question that appears simple, but becomes increasingly difficult to answer the more closely we examine it. What is the moon, really? At the beginning of this journey, the answer may have seemed obvious. The moon is Earth's natural satellite. It is a rocky body orbiting our planet at an average distance of about 384,000 kilometers. It reflects sunlight. It causes tides. It appears in the night sky. Every introductory astronomy textbook can provide those facts. Yet one of the most fascinating characteristics of scientific understanding is that the deepest questions rarely disappear when facts accumulate. Instead, they become richer. The moon remains the moon, but our understanding of what that means evolves, and by the time we gather together everything we have explored, the familiar object hanging above the horizon no longer feels like a simple satellite. It becomes something more complex, more interconnected, and in some ways more surprising than the label itself suggests. If we ask the question from a geological perspective, the moon appears as a preserved remnant of the earliest solar system. Its surface contains records extending back nearly 4.5 billion years. Ancient crust formed from a global magma ocean remains visible today. Giant impact basins preserve evidence of a violent era when planetary construction was still underway. Volcanic plains record episodes of internal evolution long after the moon's initial formation. Every crater, every mineral assemblage, every isotopic ratio contributes another fragment to an archive spanning almost the entire history of the solar system. Viewed through this lens, the moon is less a neighboring world and more a surviving document, a geological manuscript written in stone and preserved by the absence of atmosphere, oceans, and plate tectonics. If we ask the same question from the perspective of planetary formation, the answer changes again. The moon becomes evidence. It becomes a clue pointing toward events that occurred when Earth itself was young. The leading formation models suggest that the moon emerged from a colossal impact involving the early Earth and another planetary body. Whether future refinements modify aspects of that picture or reveal additional complexities, the broader conclusion remains remarkable. The moon is not merely orbiting Earth. It may represent material intimately connected to Earth's own origin story. In that sense, the distinction between Earth and Moon becomes less absolute than everyday language suggests. They are separate worlds today, yet their histories appear deeply intertwined. The Moon may not simply accompany Earth through space. It may be part of the physical legacy of Earth's creation. If we shift our attention toward physics rather than geology, another layer emerges. The Moon becomes an active participant in a gravitational system. It is not passively circling Earth like an ornament attached to a mobile. It continuously exchanges energy and angular momentum with our planet. Through tidal interactions, it raises ocean tides, deforms the crust, influences rotational dynamics, and slowly alters its own orbit. The tides rolling onto shorelines tonight are connected mathematically to the gradual recession of the Moon. The slowing of Earth's rotation is connected to the lengthening of the day. These processes unfold so slowly that they disappear within ordinary human experience. Yet, over geological timescales, they reshape the architecture of the Earth-Moon system. Through this lens, the Moon is not a destination or an object, but a process, a participant in an ongoing dynamical relationship spanning billions of years. If we approach the question from the perspective of climate, the story deepens further. Modern simulations suggest that the Moon may contribute to the long-term stability of Earth's axial orientation. Scientists continue investigating the precise extent of this influence, and many details remain active areas of research. But the possibility itself is profound. The Moon's existence may have altered aspects of Earth's rotational evolution in ways that affected climatic behavior across immense spans of time. This does not mean the Moon created life or guarantees habitability. Planetary systems are far too complex for such simple conclusions. Yet it does suggest that the Moon may have quietly participated in maintaining the environmental framework within which Earth's biological history unfolded. Through this perspective, the Moon becomes neither a geological relic nor merely a gravitational companion. It becomes part of the broader story of planetary habitability. Yet perhaps the most intriguing answer emerges when we step back and view all these perspectives simultaneously. The Moon appears to occupy multiple roles at once. It is a world. It is a historical record. It is a gravitational partner. It is a consequence of planetary formation. It is a scientific laboratory. It is a destination for exploration. It is a source of questions that remain unresolved. This multiplicity may be the reason the Moon continues to fascinate both scientists and non-scientists alike. It refuses to fit comfortably into a single category. The closer we examine it, the more dimensions of significance appear. Another way to think about the Moon is through the concept of scale. Human beings naturally experience reality through local events. We notice weather, landscapes, seasons, and daily cycles. The Moon connects those familiar experiences to cosmic processes operating across vast distances and timescales. A child watching moonlight on a lake is unknowingly observing reflected sunlight. A fisherman tracking tides is participating in celestial mechanics. A geologist studying lunar samples is investigating conditions predating Earth's oldest surviving rocks. An astrophysicist modeling orbital evolution is exploring interactions that will continue long after current civilizations have disappeared. The Moon acts as a bridge between scales, linking ordinary experience to the deepest structures of planetary science. Perhaps this is why the Moon occupies such a unique position within human culture. Few celestial objects are simultaneously so familiar and so mysterious. We see it constantly, we think we know it, yet each generation discovers new layers. Ancient civilizations interpreted its changing phases. Early astronomers revealed mountains and craters. Spacecraft mapped hidden hemispheres. Apollo returned samples. Modern orbiters detect ice and permanent shadows. Future missions may uncover entirely new insights. The Moon remains close enough to study directly, yet complex enough to reward endless investigation. Familiarity has never exhausted its mysteries. And this leads us back to the central idea that has quietly guided this entire exploration. The Moon is not what most people think it is. Not because common perceptions are entirely wrong, but because they are incomplete. It is not merely a bright object decorating the night sky. It is not merely a sphere of rock orbiting Earth. It is not merely the source of tides or the target of space missions. The moon is all of these things simultaneously, woven together into a single system of extraordinary depth. It is the frozen memory of planetary violence. It is the surviving record of ancient geological processes. It is an active gravitational force shaping Earth's evolution. It is a scientific archive preserving information that our own planet has lost. It is a world whose existence continues to influence another world. And perhaps the most beautiful realization is that all of this complexity remains hidden behind an appearance of simplicity. The moon rises quietly. It reflects sunlight. It drifts across the sky. Nothing about its appearance suggests magma oceans, orbital dynamics, isotopic signatures, tidal torques, or planetary evolution. The profound often disguises itself as the familiar. Science does not diminish that familiarity. It transforms it. Once we understand what the moon truly represents, every moonlit night becomes richer. The object above us is no longer simply a companion in the darkness. It becomes a witness to the birth of worlds, a participant in the evolution of Earth, and a reminder that some of the greatest stories in the universe are not hidden in distant galaxies, but hanging silently above our heads, visible to anyone willing to look upward and wonder what is really there. And so, as the moon continues its slow journey across the night sky, moving through the same darkness that surrounded the young solar system billions of years ago, perhaps the most accurate answer to our question is also the simplest. The moon is not merely a moon. It is one of the most extraordinary records of cosmic history that humanity has ever been fortunate enough to encounter, a neighboring world whose quiet presence contains an entire universe of stories waiting to be understood. Thank you for spending this quiet journey through space with me tonight. If you enjoyed exploring the hidden story of the moon, please subscribe to Sleepy Space. Sleep well, dream deeply, and I'll see you on our next voyage among the stars.